Alright everyone, so this will be the last video before our second test, which will be on Friday, and then tomorrow I'll go and have another Zoom call for anyone to ask any questions that they have in preparation for the test. Okay, so what we want to do is we're going to come back to limits here. And we're going to go and come up with a different way in which we could solve limits that before we could really only use algebra to solve. So, remember a while ago we'd said that as x goes to 0, the sine of x over x goes to 1. And the way we showed that one about 2 weeks ago was we went and used the squeeze theorem and some triangles and parts of circles to go and pull this one off. And this is what we could refer to as an indeterminate form. So we have 7 different kinds of indeterminate forms that are listed here. One is 0 over 0, so that's a typical one that we've dealt with, and that's also the sine of x over x one. So it just means that the numerator and denominator are both going to 0, as in this case x goes to 0. But other indeterminate forms that we could have are infinity divided by infinity, and we've seen that one a few times as well. 0 times infinity we've seen a little bit, not too much. I think a couple of the cases where we'd see that was where we were using squeeze theorem to deal with the limits. We also had infinity minus infinity, which is one we've seen a couple of times, and then the last three we haven't really seen at all. So 1 to the infinity, 0 to the 0, or infinity to the 0. The reason for these last two is that it depends on whether or not your function is, whether the base is going to 1 from below or above, and it also depends on whether the base is getting to 1 faster than the exponent is going to infinity. And the same is kind of true for the other two. Okay, so that introduces us to what's called L'Hopital's rule. So what L'Hopital's rule says is, suppose that we have two functions f and g that are differentiable around some point a, and we're looking at the limit as x goes to a. If it's the case that either f and g are both going to 0 or infinity, then the limit as x goes to a of f over g is the limit as x goes to a of f prime over g prime. So in other words, what it's doing is changing from looking at f and g to looking at their rates of change. So we're looking at more or less how fast f and g are getting to their destination, is the way we can think about it. Now, two things. One, this only works if the limit on the right-hand side exists, and then we could also do this for one-side limits or limits at infinity if we so chose. But the important thing is that this only works if you're looking at a limit that is of the form 0 over 0 or infinity over infinity. If you try this on any of the other 5 indeterminate forms, it will fail and fail spectacularly. And if you try this on something that is not an indeterminate form, it will also fail spectacularly. Okay, so let's do a couple of examples. So the first one that we'll have is the limit as x goes to 1 of natural logarithm of x over x squared minus 1. So what we can see here is that as x goes to 1, natural logarithm is going to 0, and our denominator of x squared minus 1 is also going to 0. And what we're going to say is that we're using L'Hopital's rule, so one way that we can denote this is by putting a little h over the equal sign. And then from there we're going to take the derivative of the numerator and divide by the derivative of the denominator. So we'll get the limit as x goes to 1 of 1 over x, and that's all divided by 2x. Simplifying things out a bit, we get a limit as x goes to 1 of 1/2 x squared. And as x goes to 1, our final limit is 1/2. So another thing that we could think about with L'Hopital's rule is that what this is doing is it's the quotient rule when you forget the quotient rule. So it's not actually the quotient rule for derivatives, but it is what you might expect the quotient rule for derivatives to be. Okay, so the second one. So another way that we could go and say that we're using L'Hopital's rule is to just write the indeterminate form that we have. So in this case, we have the limit as x is going to pi over 2 from the left. And our numerator is 2x minus pi. Our denominator is cosine squared. And here the numerator is going to 0, and the denominator is also going to 0. Cosine of pi over 2, or 90 degrees, that's going to be 0. So we could say that we have a 0 over 0 indeterminate form, and then we're going to go and take the derivative of our numerator and denominator. So the derivative of our numerator will be 2, derivative of the denominator will be minus 2 cosine times sine. Okay. So what we see is that the denominator is going to 0, the numerator is going to be just fixed at 2. And now we just need to figure out what sign we're going to be dealing with, because our denominator is going to 2 and the numerator isn't. We're going to have our limit going off to infinity. And because we're looking at a left limit, you could think about it as we are looking at x values that are less than pi over 2, or in other words, the angle is less than 90 degrees. So we're looking at something in the first quadrant. In the first quadrant, sine and cosine are both positive. So all of the pieces here are going to be positive, except for this minus sign that's sitting there. So we've got a positive, a positive, a positive, and a positive with this negative out in front. So that tells us our limit's going to be minus infinity. Okay, for the next one, we have the limit as x goes to 1 from the right of x over natural logarithm of x. We could go ahead and do L'Hopital's rule. We'd wind up with the limit as x goes to 1 from the right of 1, all divided by 1 over x. Simplify that out, we get the limit as x goes to 1 from the right of x, which is just 1. Okay, so hopefully you see the problem with this, and it's that we can't do this because the thing we are looking at is not actually an indeterminate form. As x goes to 1, well, our numerator is going to be 1, not 0. But our denominator will be 0. So we're going to wind up with a limit of plus infinity, because our numerator will be positive, the denominator will be positive, and going to 0. Okay, so this tells us that we do need to be really careful whenever we're doing these kind of problems, and we just need to make sure that we're actually looking at something where L'Hopital's rule applies. So we're actually looking at something that's 0 over 0 or infinity over infinity. Okay, so for the next one, we could take the limit as x goes to infinity of x squared over e to the x. Both our numerator and denominator are going to infinity, so we can apply L'Hopital's rule in here and say that we have the limit as x goes to infinity of 2x over e to the x. Well, our numerator and denominator are both still going to 0, so we can apply L'Hopital's rule a second time. And when we do that, we get our numerator is now 2, denominator is e to the x. And as x goes to infinity, we get a final answer of 0. Okay, so that tells us what to do when we're looking at a 0 over 0 or infinity over infinity case. But what we could do now is go and look at some of the other cases that we had. So the first one that we're going to have is the limit as x goes to 0 from the right of x squared times natural logarithm of x. And what we see here with this one is that as x goes to 0, x squared is going to 0, but the natural logarithm of x is going to minus infinity. So this will be an infinity times 0 case. And what we're going to do to resolve this one is we're going to go and move one of our factors into the denominator. The rule of thumb when you do that is you want to make the derivative as easy as you can. So we're going to put the x squared into the denominator by writing it as 1 over x squared. So in other words, we're flipping x squared twice, and you could go and invert and multiply this back and see that we haven't actually changed anything. We've just cleverly rewritten x squared to get this into L'Hopital's rule form. So now we have is a numerator that is natural logarithm of x, and as x goes to 0, that goes to minus infinity. Okay, and our denominator of 1 over x squared is going off to infinity as x goes to 0. So we've now got our entire expression in infinity over infinity form, so L'Hopital's rule applies here. If you just tried to do, I don't know what exactly you would do here, but suppose you just tried to do something on this with just throwing in some derivatives, it would probably fail on you spectacularly. Okay, so what we're going to do then, we take L'Hopital's rule, we get our derivative of the numerator, which is 1 over x, and it's all going to be divided by the derivative of the denominator, which is minus 2 over x cubed. Factoring and canceling a few things, we'll get minus x squared over 2 as x goes to 0, and that limit is just going to be 0. Okay, so then for our limit as x goes to 0 from the right of 1 over x minus 1 over sine of x, we'll do the typical thing that we've done, which is try and get a common denominator first. So we'll multiply the first term by sine over sine, multiply the second one by x over x to get a common denominator. So then we get the limit as x goes to 0 of sine of x minus x all over x sine of x. And now what we have is something that's in 0 over 0 form. So our numerator is going to 0 as x goes to 0, and the same is true for the denominator. So we'll apply L'Hopital's rule, take our derivatives. When we do that, we get cosine minus 1. Well, as x goes to 0, then the numerator is also going to go to 0. And our new denominator is sine of x plus x cosine of x. As x goes to 0, that's also going to 0. So we've still got something in 0 over 0 form. So we'll just do L'Hopital's rule once more. And when we do that, L'Hopital's rule a second time, we get that our numerator is minus sine of x. Okay, so that's still going to 0 as x goes to 0. But our denominator now is cosine plus cosine minus x sine of x. As x goes to 0, the x sine of x is going to go away to 0, but the cosines will be 1. So we'll wind up with a final limit of 0. Okay, well now what about if we have a base and an exponent as well? So we have, in this case, the limit as x goes to 0 from the right of x to the x. Well, the first thing that we're going to do is we're going to say, let's let y be this value. So we'll let y be the value of the limit as x goes to 0 from the right of x to the x. And then what we could do is we could just go and rewrite the expression by taking the natural logarithm of both sides. And then what we're going to be able to do is take advantage of the continuity of the natural logarithm by going and switching the order of taking the natural logarithm with evaluating the limit. Okay, so then we get that the natural logarithm of y will be the limit as x goes to 0 from the right of the natural logarithm of x to the x. Well, if we remember our rules for logarithms, we're able to pull that power out in front. So we get the natural logarithm of x all times x. Still with the limit as x goes to 0. And we want to get this into L'Hopital's rule form. So we see that the natural logarithm is going to minus infinity. The x is going to 0. So we have this in 0 times infinity form. We'll just go and slip the x into the denominator by writing it as 1 over x. And that gets us infinity over infinity form. Okay, so after applying L'Hopital's rule, we get that our new numerator is going to be 1 over x, and the denominator will be minus 1 over x squared. So simplifying this, we get the limit as x goes to 0 of minus x. And that limit is 0. Now, we should be careful at this step, because what we've said is that the natural logarithm of y is 0. But that's not actually the thing we're interested in. We are interested in y, not the natural logarithm of y. So whenever you go and do a limit like this, where you first start off by taking the natural logarithm, you just need to see what you're actually getting for the final answer. And what we found so far is the natural logarithm of our answer. So to get the actual desired value y, so the limit as x went to 0 of x to the x, we just need to raise our final answer to the power of e. So to get back y, we'll take e to the natural logarithm of y, or in other words, e to the 0, and we get a final answer of 1. So what that tells us is that the limit as x goes to 0 from the right of x to the x is 1. Okay, and then we could go and take the limit as x goes to 0 of sine of x over x, all raised to the 1 over x squared power. Well, we know that the inside part, the sine of x over x, is going to 1 as x goes to 0, but our exponent is going to infinity. So this is another one of those indeterminate forms. So we have a sign that looks like 1 to the infinity. The first thing that we're going to want to do is we're going to try and get that 1 over x squared down, and we're going to do that by taking natural logarithms of both sides. And then we're going to take advantage of the continuity from natural logarithm to switch the order of taking the limit with evaluating the natural logarithm. So we'll get the limit as x goes to 0 from the right of the natural logarithm of sine of x over x all raised to the 1 over x squared power. And then using our rules for logarithms, we'll pull that 1 over x squared out in front. So we get the limit as x goes to 0 from the right of the natural logarithm of sine of x all over x, and then the entire thing is divided by x squared. So because the sine of x over x is going to 1, the natural logarithm of sine of x over x is going to 0 as x goes to 0, and our denominator is clearly going to 0. So at this step, we'll go and apply L'Hopital's rule because we have something that's 0 over 0. Okay, and then using what we know about the derivative from natural logarithm, we'll go and do the chain rule. So we'll get 1 over the argument. So we'll get 1 over sine of x over x. So in other words, x divided by sine of x, all times the derivative of our argument. So the derivative of sine of x over x, we could easily find with the quotient rule to be x cosine of x minus sine of x all over x squared. And then we still have that derivative of the denominator, which is 2x. Okay, so then what we could do is just turn our 3-story equation into a 2-story equation and simplify it a little bit to get 1/2 times the limit as x goes to 0 from the right of x cosine of x minus sine of x all over x squared sine of x. And we could easily see that we're still in 0 over 0 form. Our numerator and denominator are both going off to 0, so we have to apply L'Hopital's rule again in this case. And what we would see from taking the derivative of the numerator and also the denominator, we could simplify it a little bit and get 1/2 times the limit as x goes to 0 from the right of minus sine of x over 2 sine of x plus x cosine of x. So one thing you want to do whenever you're doing L'Hopital's rule is after you take the derivative, cancel as much as you can, simplify as much as you can, because if you don't, you could wind up making the problem much, much harder on yourself. Okay, so in spite of our simplifications, we see that we still have something that's 0 over 0 form. Now at this step, we'll go and take the derivative of the numerator, divide into the derivative of the denominator again, and what we see here is that our numerator will be minus cosine of x, and our denominator will be 3 cosine of x minus x sine of x. So we finally get an answer. And particularly, we get 1/2 times minus 1/3, so we get a final answer of minus a sixth. And remember that we've just found the natural logarithm of the thing we're interested in, so we just need to go and raise both sides to the e. So it tells us that the original limit we were looking at is e to the minus 1/6. Okay, and then there's kind of a side bit of information. This isn't totally relevant to us, but it's more useful when you go off to Calc 2. Well, I'll just leave it at that. So we'll use the notation f is much less than g to mean that as x goes to infinity, g is growing much, much faster than f. So as x goes to infinity, g is going to be substantially bigger than f. So some examples of growth rates. So if you take a natural logarithm and you power it up as much as you like, that's going to be smaller than a polynomial term. So natural logarithms are about the slowest growing thing there is. They'll go to infinity eventually, but they're incredibly slow in getting there. An x to the p times a natural logarithm raised to some power will grow much, much faster than just the polynomial part, but that will grow slower than a bigger polynomial term. So an x to the p natural logarithm of x to the r will grow much slower than an x to the p plus s. Polynomial terms will lose to exponentials, so b to the x's, so you're going to take some number b and power it up x times, but then that will lose to an x to the x. Okay, so again, those are kind of just some interesting points. We're not really going to see them again, but you will definitely see those when you go off to Calc 2. Okay, so there will be a worksheet over this, and then as I said, I'll go and have some some office hours, so a Zoom call tomorrow for anyone who has any questions about anything relating to the test or otherwise. Okay, and I will see you all then.